But anyway, I will go ahead and show you guys one question that will be appearing that I put down on the practice exam. And it's one question, it's to kind of give you the idea of the type of problem that will appear on the timed lab. Give me 1 second. So, boom, boom. And again, as I mentioned, the exam is not next week, but the week after. So it's going to be not this week, so not next week, but it's going to be the 8th or the 9th. Now the reason for that is to give you guys plenty of time to do stuff that are like the hash table. So I will be releasing a pretty awesome assignment before the exam. And then the week of the exam, hash tables will be like the content that's covered next week. And then on the week of the exam, I'll be releasing more videos, but they're going to be on sorting, which is going to be a fairly light chapter in comparison. So it's a good place to just introduce that kind of stuff because there's going to be a lot of stuff you've seen before. Bubble sort, insertion sort, selection sort, right? Those things are all things you should have seen before or something similar. And therefore, they will be covered there. And then once we're done with the exam, we'll get to the more advanced sorting algorithms. Right in time for the break, which, of course, I will not expect anything of you over the break because you're not going to do anything even if I assigned it. So, and then after that, we'll essentially just have graphs. So now, with that said, I still have to come up with the practice exam. That will be posted next week, or I have to adapt the practice exam. You know, there's some typos in it. I want to change some of the questions. But let me just go ahead and grab one of the questions from the practice exam, which I think is a rather excellent question. It's a question that we've actually asked on final exams in the past in this class. So, which is not to say it's a hard question at all, but I'll be posting this up later. Here we go. So, but this is the type of question you'll expect on the timed lab. So in case you want to start practicing now. Okay, so coding. So write a method which, given a tree of integers, computes and returns the sum of all the integers stored in the tree. Right. Now this is a purely recursive method, but basically we provide you with a node, and we call that node root. Now remember, when we're passing it in like an instance method like this, it refers to the root of that tree or the subtree that we're currently working on, not necessarily like this dot root. Okay? And that's the type of question that you should be able to expect of the difficulty on the exam. And there's one more. I can give you another one after this to work on. So this is, and then I guess it becomes hard. Then I need to go and find some new practice exam questions. Okay? But all right. So everybody got this one down? And if not, there's going to be a video, so no worries there. Okay? So the next question, the other question that you might see something similar like, this one's a bit of a tricky one, but not like too tricky. It just requires a bit of thought. Okay? Here's another type of question of that type. Write a method which, given two trees or subtrees, returns whether or not the contents of the entire tree are identical. E.g., do tree A and tree B store the exact same data in the exact same way? And again, tree A, that could be a subtree rather than the whole tree, right? Right. Now we're basically, this is saying, does this tree equal this tree? And do they have both the same items, and are they stored like in the same structure, right? Do all the left childs and all the right childs are the same, right? Not do they just contain the same numbers, right? They also have to have been added in the same order, and the structure needs to be the same, right? So this one, and both of these, believe it or not, can be accomplished in like this one. Let's see. So the previous one. Let's go ahead and discount the curly braces, right? Let's see. 1, 2. Okay, third line for the curly brace. And then 4 lines for this one. I can get this one down to 4 lines. 7 if you want to spread it out. And this one, let's see. Let's see. This one's a bit more. Right? Let's see. 3, 6, including curly braces there. 9, because if statements. So 3, 6, 9, and then probably 10 lines over here. So they aren't really that. So these things are pretty concise if you manage to. But the trick is that they're all done recursively, right? Okay. So they're not. So these are kind of examples of the questions you would get. Okay. Now, Huffman encoding, which will not be on the timed lab, but that will be on the exam. So just keep that in mind. And again, I'll give you questions and stuff on when I issue the practice exam. Okay, so that's any questions about upcoming material? All right. So today we're just going to skip ahead, right? You may notice that it says Chapter 9, Self-Balancing Search Trees. So we're going to skip ahead and just kind of discuss what a self-balancing tree is, really. And because any tree that you actually use, like those used to implement sets of maps, are going to be using a self-balancing search tree. And really all I'm going to go over in this chapter is, in this like little lecture over here, is this. Just enough to introduce the content we need for an in-class exercise. And then just let you know that these things exist. All right? Right, so the idea here is that the binary search trees that we've learned so far, how well they perform is proportional to the height of the tree, right? So a full binary tree of height k, right? Sorry, can hold k to that should be a perfect there. That's a typo. A perfect binary tree of height k can hold 2 to the k minus 1 items. If the search tree is full and contains items, the expected performance is log n. However, if it's not full, well, not perfect actually, then the actual performance is worse than expected. Let's look at an example. Here are 2 examples of unbalanced trees. All right. These are binary search trees that are unbalanced, and their search times as a result are log n. Are not log n. They are O of n. Right. Everybody see that? Okay, so this one, right, this is if I added 1, 2, 3, 4, 5, 6, 7, 8, 9 in order. And that's kind of an unrealistic example. A realistic example might be something like adding the quick brown fox jumps over the lazy dog, right, all in order. And this is a unbalanced tree that might form as a result, right? Notice that it's mostly one line and any branch is just kind of a leaf. Anything that branches off this singular path right over here is just a leaf, and it doesn't really so anytime we go left and right, we aren't actually cutting down our search space by half. We're just terminating our search, and we're not really doing it in a consistent manner. So that's kind of the issue we have here. So what all these trees have in common is something called all these self-balancing trees have in common is that they all have this different strategy to detect whether or not they're unbalanced or not. Right, that means do my subtrees differ by a height that's acceptable or not, right? Like a red-black tree will let it get quite a bit more out of balance than an AVL tree will, but never such that it will be more than log n time. So the way it keeps everything under control is that once it detects something has gone wrong, it does what's called a rotation. Now this is demonstrating, I believe, a right rotation here, where it goes left to right. So here, we are doing a right rotation around 20. And the way that works is that 20s will go to the right. It will become the right child of the root, hence right rotation. And what it does is that it tells its left child to become its root. It will take its left child's right child as its left child, and then move off. So that's a lot. That's a mouthful, right? Right? But fortunately for us, Wikipedia is amazing, and we're going to see that they have amazing graphics and stuff, and step-by-step instruction on how to perform this. Now, this operation does take about 4 lines, including a return statement, so it's not actually hard at all, and that's the target what we're doing for today. But essentially what this does is that when we rotate right around 20, this brings 10 up to the root, right, and 10's right child becomes 20's left child. So see that over here where we attach this child over here to 20, and it moves down. And notice that this operation, interestingly enough, this operation will preserve the balanced property and also the binary search tree property. Sorry, it will preserve the binary search tree property, while it kind of like evened out the layers here, right? As we can see, it's a much more aesthetically pleasing tree. It's a much more balanced. And the algorithm is as follows. So first thing we want to do is remember what your root node is, right? So remember the value of root.left over here. So set my left child as a temporary node. Then I'm going to grab my left node's right child. Okay, so now I've got my trees kind of broken in this form. Then what do? I set temp.right to root. I take this guy and say, actually, this guy should move up to be the root. And now we make temp the root of the tree. And so now the original root of the tree has become the left child, and the left child has become the root. See, it's just 4 steps. Oops, sorry. That was, and then, so that's really, and then if we reorder it, it now looks like this. So let's go ahead and take a look at Wikipedia to kind of get a few better animations. So tree rotation, which sounds like right? It's got an entire article on it, right? It says, okay, so obviously since this one has Greek letters, then it's obviously a super complicated operation, right? No, it's not really. It's one of those cases where they use Greek and it makes it sound way more intimidating. But here you can do a right rotation, and then you can do a left rotation to undo that right rotation on the same node. I personally prefer this operation that shows this over here, this animation over here that shows what's going on. So here, if you want to do a left rotation, we declare 2 nodes, the pivot and the root. And notice that basically this node over here, this subtree over here is what gets passed back and forth between them. And the reason for that is that notice that this is everything greater than A, but because it's less than B, because it's on B's, as we'll see again, it was on B's left side, right? This is on B's left side, so it's all less than B. So it's all perfectly fine for B to take that as its left child, right? And it's all greater than A, so it's all fine. So it's fine for it to end up right here. So that's why this preserves that property. Now let's see. Another. This is the one that basically I think if this is something similar to what I've seen. So we declare, so this is another picture of that. We declare, again, the root that we're rotating right along. We declare the root to be, we take our root, we have what we call the pivot, which is what's going to come up. We grab the pivot's right child, and the pivot's right child becomes the root. And then as a result, this just restructures so that pivot is now the root of that subtree. Now the final thing to do that just kind of that's got completely glossed over here is that actually, if this is if this is a subtree that we just rotated, then we need to inform our parent. So we return basically what my parent's new child should be, because that just changed. So we return that to our parent. And then again, you can rotate left, which does the same thing. But and that's just essentially we just flip our left and right around. So I'm just going to be focusing on the right rotation for that, for what we're going to implement today. So any questions on this so far? So now now this is used in all sorts of trees. This is used in the AVL tree, which is named after these authors, and the tree is known by their initials, right? And it keeps track of the difference in height between each subtrees. And then as these things become more and more out of order, I'm not really going to go too much into it. You can read up on it yourself if you're interested. As these things become more and more out of order, it figures out you end up with 4 different conditions, and then it figures out what series of rotations it needs to perform. Does it need to perform a left-left rotation? Does it need to perform a left-right rotation, a right-right, or a right-left, right? Which combination of rotations along which nodes will bring everything back in order. Now, because a rotation is a constant time operation, it doesn't matter how big the tree is, right? They don't really add, and so long as you don't have to do more than log n rotations to fix something, it's going to be a lot. Then add and remove are going to still be log n time, right? Adding something or removing something might cause the tree to become unbalanced, and then you just fix it with at most log n rotations. Now the one I learned, you either typically learn this, an AVL tree, and I'm not going to put you through this. I prefer to focus more time on hash tables. Another thing you might be asked to do in a data structures class, depending on what you're asked for, is to implement something called a red-black tree. I'm not a big fan because the add method's like 43 lines. It's kind of, but it's a very good learning concept for these things. And basically you color nodes, and you have these rules that the node is either red or black. The road is always black. A red node always has black children. Nulls are considered black nodes. And that any path needs to contain the same number of black nodes. Any node from a root to a child contains the same number of black nodes. We determine height only by counting black nodes, and then we just have these rules about how things are added. And then when you get one of those rules broken, there's a specific way to fix it. And there's a specific types of rotations to do to fix it. So again, I'm just breezing past these, and these are more to tell you that these concepts exist. And they all basically have, depending on how things need to be fixed, they all have specific ways of showing that we have to fix it. And you have and these are things where you'll actually care about what your uncle is and those kind of things. Let's see. Now, the only other thing I want to show you that's kind of unique about other self-balancing trees is one that kind of breaks the idea that we've been having that a tree can only have 2 nodes, right? Which is a 2-3 tree, which is made up of either 2 nodes or 2 or 3 nodes. Which 2 nodes have 2 children, 3 nodes have 3 children. The way it works is that a 2 node works exactly like it would in a binary search tree. Everything less than x goes to the left. Everything greater than x goes to the right. In a 2-3 tree, you have two values, x and y. Everything less than x goes to the left. Everything greater than y goes to the right, and everything in between them goes in the middle. Okay, so instead you have 3 paths to go down. And then, so the way this works is that we kind of add nodes, and then as needed we can basically make nodes kind of fill, and then we can insert something in and then have to split it and reorder stuff in the tree. But it basically keeps the height of the tree down, and it provides a way to go over different segments, go down different branches in a more efficient manner. So this is more to let you know that this exists rather than to tell you, than to say this is, than to go over it. They can be a bit complicated, but this is more to let you know these exist. But the big thing that these all do is that we can rotate stuff to fix height if we need to. All right. So for today's assignment, what I want you to do, or for today's in-class exercise, what I'd like you to do is to code up a right rotation. Okay. So now I don't want you to go into this completely without any code. So if you go to the GitHub link, go to data structures, then you should be able to go to let's see. If you go to data structures, you should be able to look and see the trees package, which will have the binary tree code in there. And what you can do is you can add to that class the left rotation and the right rotation. I'm sorry, just the left rotation, and then test out to see that it works. So that's your in-class exercise for the day. Submit it, and it's worth 5 quiz points, so just a great way to bolster your quiz grade. We'll do some, so that's what we'll be working on today, but mainly you don't have to do the left rotation because it's kind of trivial to figure out, but here's kind of the algorithm for the right rotation on the Wikipedia page. Again, pictures are on the Wikipedia page. Python code is on the Wikipedia page, although that one's a bit more obscure because it deals with Python and tuples, so that might be a bit harder to read unless you understand what they're going for. And then here's some more pseudocode, right? So again, so for this one, I highly suggest, by the way, that you work in pairs. So I would pair up with whoever you want to work with this, and then submit your code in a Dropbox that I put up. All right, everybody clear on what we want to do today? Okay, so we go ahead and get